Welcome! We're going to take a look at the Charpy Impact Test, also known as the V-notch test. The purpose is to determine the toughness of materials under impact in multi-axial loading, for which we'll use a pendulum impact tester. Before the test, the pendulum must be brought to the starting position so that it gains potential energy. In order to first verify the pendulum's proper functionality, a free swing is performed. The pendulum display must remain at 0, since no potential energy is lost when there's no test specimen to impact. The compensation of the friction is ensured by regular calibration and maintenance. The first test with an ISO V specimen made of C45 can begin. The ISO V specimen has the characteristic middle V notch. The specimen is centered and placed in the machine with the notch facing away from the hammer. When the test starts, the hammer drops down and its striking edge hits the test piece. Part of the potential energy is absorbed by the specimen upon impact, breaking it in two, which is why the hammer no longer swings back up to the same height it was released from. This absorbed energy is what's measured on the indicator and is referred to as Charpy Impact Energy or work, and is usually labeled as kV. This is the energy needed to break the specimen. In this case, it was only 15 joules. Let's look at the basic principle of the Charpy Impact Test. At its initial position, the pendulum hammer only has potential energy. This energy can be calculated with the formula mgh, where m is the mass of the hammer, g is the acceleration due to gravity, and h is the height of the hammer head. After the pendulum is released, it swings downward. At its lowest point, it has now converted all its potential energy into kinetic energy, and that's precisely when it hits the specimen. The pendulum hammer swings through and reaches at the reversal point a lower height than the one it was initially released from. The difference between the initial and the final potential energies is the energy that was passed onto the specimen in the form of the Charpy impact energy. The first specimen shows almost no signs of plastic deformation. You can see that the fracture surface is almost flat, slightly glittering even. Both qualities are strong indicators of brittleness, so now we know that this material can only absorb a small amount of impact energy. The second test is carried out with a V specimen made of 1.4301 material, a type of stainless steel. This specimen is also placed centered in the support of the machine. The display is again set to 0. When the pendulum strikes, you can hear the difference in pitch upon impact from the first test, the second having a significantly lower pitch. The specimen also achieves significantly more notch impact energy, namely 153 joules. The second specimen is also broken into two parts, but the fracture surface shows a clear deformation. It has been peeled open, so to speak. There is a great zone of plastic deformation, meaning that the hammer can even push the specimen between the supports before reaching final rupture. A direct comparison shows the clear difference. The stainless steel absorbs significantly more impact energy than the C45, showing a tough, highly ductile behavior in the Charpy Impact Test. The third test is performed with a specimen made of the material AlMgSi1, a type of aluminium. The specimen is again centered in the supports and the display is set to 0. The test is started, and on impact you can hear that the bang has a high pitch, similar to the first test. The specimen has a V-notch impact energy of 41, scoring between the C45 and the 1.4301. The specimen once again broke in two pieces. In a direct comparison of the three samples, you can see the similarity to the stainless steel fracture, shape and surface, and the difference to the C45s. So the value of the impact energy alone is not sufficient to judge the toughness or ductility of a material. The fracture shape is also important. This is especially the case when comparing different material groups, as we're doing here. Let's now look at the temperature dependence in the Charpy Impact Test. The test is not only performed at room temperature. Materials with a body-centered cubic structure show a strong temperature dependence in their V-notch impact work and exhibit an S-shaped curve with a steep slope. This is referred to as the transition temperature. In the upper shelf, the same material can absorb a large amount of V-notch impact energy. In other words, at this temperature range it's tougher and has more of a ductile fracture. In the lower shelf, it's more brittle and can absorb way less impact energy. In contrast, materials with a face-centered cubic structure have a virtually constant Charpy impact work, so they can absorb pretty much the same amount of energy regardless of temperature. They remain just as ductile and tough throughout, and they are therefore very suitable for low temperature applications. If the material state is changed, for example, by hardening in the case of steel, or if we have a steel with a high carbon content, the kV shifts downward and the material reacts very brittle regardless of the temperature. Finally, let's move on to the instrumented Charpy Impact Test. In this variation of the test, we not only measure the V-notch impact energy, but also the force curve over time via a force transducer in the striking edge. Analyzing this curve can also help us determine the fracture behavior. If we have a very steep force drop after the force maximum, that's a specimen with low Charpy impact work exhibiting a brittle fracture. If we have a slow drop in force at first and then a steep drop, we can determine a mixed fracture. If the force drops gradually, we have a deformation fracture with a high impact energy, that is a tough or ductile specimen. The relationship between the force over time and the Charpy impact energy is as follows. The impact energy is the integral of the force time curve, i.e., it corresponds to the area under this curve.